This video, we're going to look at properties of solution, and specifically, we're going to address and delve into colligative properties. Now, colligative properties are basically properties that are dependent on the number of dissolved solute particles and not necessarily the chemical identity. So it's really just more dependent on what's dissolved, like or how many ions you have that's dissolved into the substance versus what type of ions are in there specifically. All right, and so let's jump into what colligative properties and what changes. So the first colligative property is vapor pressure. All right, and so let's just kind of remind ourselves what is vapor pressure. So vapor pressure is basically the vapor pressure of a liquid depends on the equilibrium between molecules entering and leaving the liquid surface. And so, for example, if you have a closed container, right, and then you have some amount of liquid, all right, only particles that have enough energy at the surface will go to its gaseous state, right? But remember, this is an equilibrium. So as you have substances going up into the gaseous state, then you also have some of the same substances go back down to the liquid state. And it's at equilibrium. So it simply means that the same amount of gas that goes into the gas state will be the same amount of gases that will go down to the liquid state. So that's what it means for something to be equilibrium. It's going on at the same rate. So overall, there's no net change. Okay. And so that's your vapor pressure. Now, for a colligative property, so let's just say if you have another substance, a solute that's dissolved into this water here, or this solvent. All right, now this substance, all right, may not have the same type of vapor pressure. It may have a much higher boiling point, or whatever the case may be, right? Now, what's going to happen is that if this substance here does not as easily vaporize as the other substance previously, then you're going to have less gas have the ability to vaporize, and then less gas will if you have less gas able to vaporize, then you're not going to have as many able to go back to the liquid state. So thus, in this case, is that the vapor pressure decreases. So when you have something that's dissolved into water, if you have a solution, then the vapor pressure will decrease. So a solution vapor pressure is lower than the pure substance vapor pressure. All right, so not as much molecules will be able to go to this gaseous state. All right, so that's the way that you kind of have to think about it. Now, as I said before, when it comes to colligative properties, it doesn't matter what gets dissolved in there. It just matters about the concentration, how much ions are you making. And so the more concentration of the solute you have, the more you're going to affect the vapor pressure of the total solution. And so the vapor pressure will decrease because you have a substance in the liquid, in the solvent. So another colligative property, meaning a property of a pure substance that get affected when something is dissolved into it, is boiling point. And so as a consequence, as the vapor pressure lowering for a solution, is that because the vapor pressure lower, so not as much gas, not much liquid was able to turn to the gas, then that simply means then that the boiling point of the pure solvent will be, or boiling point of the solution will actually be higher than the pure substance or the pure solvent. All right, and so it needs more energy in order to get that substance to go from its solid state, from its liquid state to its gaseous state. All right, and so, and we can actually quantify this, especially when we were dealing with water. Okay, and so, and just kind of bring it back so I could kind of write this. So colligative property, the boiling point, as I said, will increase. All right, so and it's going to be higher. The boiling point will be higher compared to the pure solvent, right? So if it was just water, then the boiling point is 100 degrees Celsius. But if you have something else that's in there, all right, you dissolve a strong electrolyte in there, depending on the concentration and what, of course, then the boiling point of water will actually be higher than 100 degrees Celsius, all right? And then we could actually quantify this. We can actually calculate this, all right? And so it just turns out with water, particularly, anytime you add 1 kilogram of solute in water, all right, the boiling point of water will increase by 0.51 degrees Celsius. All right. And so if you were to try to figure out the how much the boiling point will change, all right, so if you're trying to figure out how much the boiling point would change compared to water, then what you'll do is 0.51 degrees Celsius of kilograms of water divided by the moles of the particles, all right, times the moles of particles divided by kilograms of water. All right. Let me go ahead and try to make this makes more sense of this for you. All right, so let's go ahead and look into this example here. So the question asks, what is the boiling point of a solution of 0.7 moles of KBr in 1.0 kilograms of water? All right, so we want to know what's the new boiling point now that you have this solute that's dissolved into water. Okay, and so what we could figure out, and I showed you guys the equation of this a little bit earlier, is that the equation, now I'll just write it again, that the delta T, all right, the change of temperature due to boiling is equal to 0.51 degrees Celsius kilograms of water over moles of ions. All right, this is the entire unit. All right, the unit is degrees Celsius kilograms of water per mole ions. All right, so don't get that confused. That's just the unit. All right, and then multiply by the moles of particles, all right, divided by the kilograms of water. All right, how much water do you have? All right, so let's go ahead and kind of plug and chug what we see. All right, so what we have here, we have 75 moles of potassium bromide and 1 kilogram of water. Okay, and so I'm trying to figure out the delta change of the boiling point. Okay, so I have that it is 0.51 degrees Celsius, and the units is kilograms of water per moles of ions. Okay, all right, so I need to figure out how many moles of particles I have, or the moles of ions I have. Now we have to consider this before you just start plugging in numbers. All right, KBr is a substance that consists of 2 ions. All right, so if we're trying to figure out how many moles of ions you have, we're going to have to multiply this number by 2. All right, because if you notice, all right, you have 2 moles of ions for every 1 mole of potassium bromide, because potassium bromide breaks up to potassium ion and bromide ion. All right, so you have 2 different moles of ions here. All right, and then we could use this number here where it is 0.75 moles of KBr per, all right, kilograms of water. And what's the kilograms of water? In this case is 1.0 kilograms of H2O. All right. And so then when we plug this into the calculator accordingly, then we see that the change of the boiling point in this case is going to be 0.77 degrees Celsius. So now the question is, what is the boiling point? What is the new boiling point? Well, we know that the boiling point of water is 100 degrees Celsius. Well, then we just have to add this number to it. And then we see that the new boiling point, when you add potassium bromide, or that much potassium bromide, is 100.77 degrees Celsius. So freezing point is another colligative property that's affected by ions dissolved into a solvent. All right, and so much like how solutions they have a lower vapor pressure than their pure solvent counterpart. Also, they have a higher boiling point versus its pure solvent counterpart. They also have a lower freezing point. Okay. And this we typically take more advantage of. There's a lot more real life applications when it comes to this colligative property. Okay, it's like, so for example, motorists in cold climates particularly, they tend to add antifreeze into their engine systems. All right, antifreeze basically, when with enough concentration, will actually keep water from freezing at a particular temperature. So typically, water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. Well, if you add antifreeze, then water will freeze at a much lower temperature, which that works well, because if not, anytime it is but 25 degrees outside, we're pretty much screwed. And also, like, let's say, when there are icy roads, it snows, and we know that the temperature is going to stay below the freezing point of water. Well, typically we will sprinkle salt on these roads. Why? When you sprinkle salt, you are adding a solute to the water solvent. By adding the solute, you are going to essentially lower the freezing point of water. All right, so water will so at a certain temperature, it will not remain as ice, but then it will be liquid water, which will make it much more safe for people to drive on the roads. All right, now how does this happen, and how does this work? Well, if you consider what's happening within this container here, right? When you have something becoming a solid, right, you have these substances. And so let's just say I'm really zooming in, right? The substances, when they become solids, intermolecular forces are at its strongest. All right, and so it's interlocking all these molecules together, and so that way they have a lot more rigid. It's a lot more rigid, and it forms this crystalline structure, right? And thus you have this solid. But when you have a solute, what happens is that the solute kind of gets in the way. Okay, and so because the solute kind of gets in the way, and I'm kind of racist this a little bit, I was a little bit sloppy, but hopefully you get the point that the solute kind of gets in the way of these intermolecular forces to be formed accordingly. All right, and so because the solute is in the way, then these intermolecular forces cannot be formed the way it should. All right, and so thus it doesn't freeze. All right, it doesn't become a solid as easily. And the way for that to happen, that then we have to lower the temperature even lower in order to get the solvent to freeze accordingly. Okay, and so much like freezing point, we could also calculate the change. Much like boiling point, we could also calculate the change of the freezing point once we add a particular solvent, a solute, right? And it turns out, at least for water, right, for 1 kilogram of H2O, the freezing point will be lowered for every by 1.86 degrees Celsius. All right, for every 1 mole of solute. All right, so for every 1 mole that you add in there into 1 kilograms of water, the temperature will decrease by 1.86 degrees Celsius. All right, so ultimately, the change of the freezing point of water will be equal to negative 1.86 degrees Celsius kilograms of H2O. So this whole thing is a unit, moles of particles, all right, or ions, okay, times by the mole of particles or ions divided by the kilograms of water. Okay, so that's the equation there. Okay, so let's kind of look into an example. So the example, the cells of a tomato contains mostly an aqueous solution of sugar and other substances. If a typical tomato freezes at negative 2.5 degrees Celsius, what is the concentration of dissolved particles in tomato cells? And then the units I wanted in is moles of particles per kilogram of water. All right, and so if we think back to our equation, right, where delta T freeze is equal to negative 1.86 degrees Celsius kilograms of water per mole of particle times moles of particles. Oh, put this in the wrong spot. Moles of particles divided by kilograms of water. All right. So now when we're thinking about this, let's look at what we have. So it tells us that that it freezes at 2.5 degrees Celsius. All right. And then we're looking for what is the concentration of the particles in tomato cells in moles of particles per kilograms of water. And so the good thing is this is this right here. So we're solving for that part, right? We already have our constant. And the cool thing is we know what's the temperature it freezes, right? The tomato cells freezes, and we know the temperature in which water freeze, a pure solution of water freezes. All right, and so if we're trying to figure out what's the difference, right? So I don't know why I keep on doing that. The delta change temperature that water freezes is essentially it's the freezing point of water minus the freezing point of when that substance changed. So it's going to be 0 minus 2.5. And so we find that the change is also 2.5. And so I could actually plug this number here. And so if that's the case, then it is, and I'm going to simplify this so that way all the units are not in the way. So it's negative 2.5, that's your temperature, degrees Celsius, is equal to, actually I'm going to keep the units so that we can see how everything ties up. Negative 1.86 degrees Celsius kilogram H2O over moles of particles, right, times, and really this is what we're looking for here. And so if we divide this whole thing out, right, including the units, I know this probably looks bad, but including the units, all right, all this cancel out, we could place this here, okay? And so the degrees Celsius is going to cancel out, and all we're going to have is this left. And actually it's going to be flipped, really. And so negative 2.5 divided by negative 1.86, we see that we got 1.3 moles of solute particles divided by kilograms of H2O. All right, so that's how you will figure this out.